Welcome to the 5th tutorial of the RISC-V Architecture and Assembly Language series. This section will look at B and J type instructions, namely branching and jumping. This was covered to some extent in tutorial 1, and here we will give a recap with some hands-on examples. Branching and jumping gives us the ability to alter the program flow. This is the basis of decision-making, and it's akin to for next and do until loop constructs that are found in higher-level languages. Recalling the format of the B-type instruction, we can see the breakdown of the bit fields. The format here is branch on some condition which compares registers. If the condition is met, then the flow will branch to a destination specified in the immediate field. Since the addresses are aligned on even boundaries, the least significant bit of the immediate field will always be set to 0. This means there is no need to waste a bit recording its value. Instead, its bit position can be used to record an extra immediate bit. Our range is then 2 to the power of 13, giving a wider range. An example is branch not equal. Here branch if T0 is not equal. Here branch if to register X0 to the label put it. The bit field for this instruction is hex FE029AE3, as shown above. In this example, the instruction is executed when the program counter is at address 10104X and the destination address is at 100F8X. We can see immediately that since the destination address is lower than the current contents of the broken counter, the branch will be backwards. Referring to the earlier diagram, the immediate value is binary 1111111010. The sign bit is negative, so using 2's complement, we can see that we need to step back 12 decimal places. This can be verified since adding 1100 binary to the immediate field gives the result of 0. Note that the carry is lost from the most significant position. Don't forget about immediate's implicit bit 0 when performing this calculation. Next, we'll look at the J-type instructions. The example shows the instruction JAL0 mylabel. In this example, the program counter is at hex 100C0, and the label itself is at hex 100D4, which is a forward jump. Now J-type instructions do not depend on any particular condition, and therefore they are unconditional by nature. Jump instructions can go to a particular region of the program, and they may or may not require returning to the location where they jumped from. One situation would be if the program required input from a user, it would then jump to the input routine, load the user's data, and then return to continue processing. If a jump was made to a program's exit point, then it would have no need to remember where it was prior to the jump instruction. The instruction JAL jump and link will jump to an address and store the return location. There are 20 bits, including implied bit 0, available for the immediate bit field of JAL. The RA return address register is normally used to hold the return address, which is the address of the current program counter plus 4, which means that this points to the next instruction to be executed. The pseudo-instruction J can be used, which equates to jump and link 0 register to immediate. Now since the 0 register is hardwired to be 0, the return address is not stored. There is also a jump and link register instruction which is similar, but used as a register with an offset rather than the large immediate field used with JAL. Here, the regular I-type 12-bit immediate field is used as the offset. The instruction RET return equates to JALR X0 with the RA register. So it jumps to the value stored in the RA register since the offset was 0, and we used X0. Now, a note here about the disjoint immediate fields in RISC-V. The reason that this is done is actually fairly smart. It does this to keep most of the fields consistent across the different instruction types. R and B type most commonly use bits 24 through 20 for source register 2 and bits 19 through 15 for source register 1. Bits 11 through 7 is the common bit field designation for R-type, I-type, and J-type instructions, and this consistency will allow for simpler instruction decoding. A summary of the JAL and JAL instructions is shown here. Note that JAL uses program counter relative instructions to generate position-independent code. Since the code works with addresses relative to the counter, the code is agnostic as to where it's placed in absolute memory. Here, we'll give an example for the instruction BLT. This will perform a branch if the source register 1 is less than source register 2 with an offset. Other comparison operators are shown along with their complementary unsigned variants. Using the JAL instruction with the 0 register will not store the return address, so JAL0 my label will unconditionally jump to the label without storing the return address since X0 is not writable. This could be dangerous if a subsequent return was issued. JAL differs in that it uses a target address made up of a register plus an offset. The instruction JAL0 with an offset of 0 for the I register will simply return the address in the I register. A summary of the actual and pseudo branch equivalents is shown D here along with the jump instructions. The listing will illustrate how to use a loop counter to generate squares for the first 20 integers, and we're going to cover this using GDB in the hands-on section. So you can look at the code beforehand and see if it makes sense. There is a program flowchart coming up which we'll cover. So the diagram illustrates the flow of the squaring program. This may be of some help. The first event is to jump to the called squareIt. That's event 1. Once this has been completed, the return instruction, at event 2, will cause a jump back to the next instruction after the initial jump to squareIt, where it continues processing. This is shown at event 3. Alright. Now it's time to look at some of the hands-on instructions in more detail. First of all, let's just have a look at the program listing shown. We met this one before, but now we're going to use GDB to go through the program steps. We're going to set up a counter here with a value of 20 decimal in register T0. Next we'll initialize register T1 with the value 1, and then we're going to keep incrementing this value until we reach the value 20 corresponding to the 20 integers that will be squared. Ts will introduce branching by performing a comparison with the branch if less than instruction, and we'll also show branch if less than and link. JAL instruction with the return address stored in the X1 register. After the program has calculated the squares, it will return using the jump and link register JALR instruction. So as we start working through this, we'll calculate the squares of the numbers right up to 20, and each calculated square will store the values in the address of the location, store squares. Let's exit out of the editor. And we'll assemble it and link it using the make target file script that we covered in an earlier tutorial. And now we'll run GDB. Alright, set a breakpoint with B_start and then R to run the program. So use the step command rather than next because we want to enter the routine. The first part sets up the T0 register with the value 20. And then register T1 is initialized here with the value 1. We're going to store the location of the store square routine into register A0. So we can actually see from the value now stored in A0 that the location where we're going to start storing our squared numbers is going to be at hex 1111C. So now we've entered the routine which came from the jump and link instruction. Note that the RA register is used here to store the return address. So we have now jumped to the squareIt routine. And if we look at the address held in the RA register, it is hex 100FC. So this is where we are going to jump back to after the squareIt routine has finished. Okay, we're in the routine to square the numbers. we multiply the contents of T1 by the contents of T1 and put the result in T2. So initially, T1 has the value 1. So this is going to simply multiply 1 by 1 and put the value into register T2. So there's T2 shown here. And you can see that it holds the value 1. Now we're going to store this value as a half word consuming 2 bytes. That's what store half word sh instruction does, placing the value held in T2 into the memory address pointed to by A0 with an offset of 0. Now we do not want to overwrite this value with the next result, so we bump up the pointer by 2 so that it will point to the next half word location. We're incrementing by 2 since we are using 2 bytes to store each of these results. At this time we're pointing to the first location in store squares plus 2. You can now see that since A0 is pointing to the next storage address. After this then, we want to increment T1. It was initially seeded with the value 1, now it's at value 2. Now with the BLT instruction, if the value if is less than T0, which we first set up to be 20, then if the condition is true. We're going to branch back to the beginning of the square it routine. This will continue looping until the condition is false, in other words when the value in register T1 is no longer less than the value in T0. At this point the program will use the jump and link register instruction to jump back to the address held in the RA register. And it will then execute the exit system call. So we'll continue with a few iterations and we'll skip the next few cycles and we'll return when the program has calculated all the squares. Okay. So now we've completed the loop and T1 has reached the value of 20. So this condition, branch if less than T0 to the label square it, is no longer true. This means that we can now perform a return. So the program executes the jump and link register instruction, where the return address is held the return address register, which is here. After we've executed that instruction, and we've come up to here. So if you recall, this was the point after the JAL instruction which caused a jump to the square it routine. After this we are ready to execute the system exit system call to terminate the program. But before we do that, let's have a look at our store squares memory location. If you recall from an earlier tutorial covering GDB, the X command is going to show us the memory. Now we can show the 20 values in half-word format, and also we'll display them as base 10 numbers. So we'll tell it to look in the location store squares with the GDB command shown. And there we go. So the first location of store squares is 1, and then we increment it by 2. Next we have 2 squared, which is 4, 3 squared, which is 9, 4 squared, all the way up to here. So these are the calculated values here, and you can actually see the store squares is at the location hex 1111C, which can be confirmed by issuing the command info variables within GDB. You can see the other variable addresses here as well. You may have noticed that looking at the squares, we should have branched with 21 rather than 20 because we only computed the first 19 squares. That's easily rectified as an exercise. Okay. So let's quit that program and there we go. I would encourage practicing more of these instructions with the branch and jump commands as they are ubiquitous in real-world coding. I will finish with a code listing that crashes when executed. It should not be too challenging to spot the deliberate error. This concludes this fairly short but hopefully informative tutorial. We have now concluded tutorial 5. Next, we are going to move on to tutorial 6, and we will study areas like the stack and macros. Functions will be covered in more detail. Again, thanks for watching. And you can check out my website risccomputing.com if you want to download some of the written PDF material, which will supplement this. Thanks again and see you at tutorial 6.